My name is Natalia. I'm just finishing my first year of my PhD at Stanford University, and I'm going to present some work that I did for a rotation project last winter quarter with my co-advisor, Professor Eric Darve, and also Marta and Dr. Giusti and Dr. Garappa. This work is definitely not quite as fleshed out as some of the bigger projects we've been seeing, and I'm much less knowledgeable, but hopefully this can still be interesting. So this work is about using the Riesz potential as an inverse operator for variable order fractional Laplacians. Great. So this work is mostly concerned with equations like the Poisson equation that involve a variable order fractional Laplacian, like I've shown at the top here. This type of equation appears, or this operator, the variable order fractional Laplacian, appears pretty frequently in governing physical relations for anomalous phenomena, including these examples that I've listed here. And it appears in variable order form, where this exponent s can vary over the domain in applications that concern turbulence, subsurface transport, and gravitational fields, which is the application that we looked at for our problem. We take an approach that involves transformation to Fourier space and a spectral representation of the operator, which is well suited to other spectral approaches that are becoming more common in modern physics. And we also provide a method to handle orders of the Laplacian that are larger than 1. So between 1 and n, which is like the dimensionality of the problem, which for us is 3/2, which up until now has only been somewhat sparsely studied. Okay, so kind of the main idea of the theory is to think about the Laplacian in Fourier space. And so for the regular Laplacian, which just involves the second derivative in Fourier space, is just a multiplication by negative k squared, which is the frequency, and that's what's shown here on this slide. And so kind of extending on that idea and using arguments that involve Green's functions, you come to this Riesz potential, which acts as an inverse operator to the Laplacian and can also act as an inverse operator for the fractional Laplacian of a variable order. And so that's what I've shown here in this first line. The Riesz potential can be expressed as convolution with a kernel k of s, which is going to be depending on s, which is the order of the Laplacian. And so by applying this convolution with this kernel to both sides of the equation, we're going to hope to isolate this f of x and solve the problem in that way. So I did this just in MATLAB. So the code it's up on GitHub, and it should be really easy to run if you have MATLAB. It only requires, I think, the curve fitting and also image processing toolboxes. So the user inputs s of x, which for now has to be radially symmetric. And so this is basically an expression that describes how the order of the Laplacian varies over the domain. And the code can also be pretty easily modified to take k of s as the input, which is the kernel that you use for the convolution, if that's more convenient. The user also inputs the domain size, what we call the source, which is this g of x. So in the gravitational potential problem, that just is the mass distribution. And so like the g of x is just how large is this mass distribution that you have. And then the cell size for the discretization of the domain. And then the code outputs k, the kernel, the Fourier transform of it, the gravitational potential, which is the solution to the problem, the f of x from the previous slide. The orbital velocity, which for the gravity problem it's a kind of a quantity of interest that can be observed experimentally, and also comparison to an analytical solution that one of our collaborators was able to arrive at for a constant s. Okay, so just to kind of quickly run through what the code is doing. The first thing it does is compute this kernel k and also the source function g over the domains, and then do some processing on them to prepare them for the convolution step. So that includes zero padding and also shifting the arrays such that they're in an origin first configuration instead of origin centered. Next, we do the Fourier transforms of both functions, which is this middle panel here. So yeah, we started here, shift the origin, and then Fourier transform. Then we execute the convolution, which now that we're in Fourier space is just a multiplication to arrive at the solution I of k, or f on the other side, on the other slide. This is in Fourier space, so then we have to do an inverse Fourier transform to go back to physical space, and then one more time shift everything so that the origin is at the center again. So we came up with a couple of different ways to do the Fourier transform. Our first approach was just to use MATLAB's FFT function, which does a discrete Fourier transform of k and also of g on the Cartesian grid according to like this formula that I'm sure you're all familiar with. But in cases where the kernel doesn't sufficiently decay on the domain, this approximation of the Fourier transform integral isn't converged, and therefore it's inaccurate. And so in these cases where k doesn't decay, which is also the case when s is greater than 1, we had to come up with a different approach. And so to do that, we looked at a different way to do this Fourier transform kind of more manually, using the radial definition of the Fourier transform, which is shown here. And so still here you have the problem where if k is not decreasing, this integral is not going to be defined. And so to handle that, we include this regularization term, e to the negative lambda r. And as lambda goes to 0, this approaches the true Fourier transform, and then we can evaluate this integral over a much larger domain, which allows us to properly compute the Fourier transform. And we do this basically by always computing like an increment of the integral in steps of 2 pi over k until the contribution from the integral is so small that we can say the Fourier transform is converged for that value of k. And so these are just a few of the results. So this is the source that the user would input. So this would be like a, let's say like a sphere centered at the origin. This is the kernel that is going to be convolved. Then we would return, this is just the same kernel in 1D, it's Fourier transform here. And then this is the gravitational potential, which is the solution. That's the result of the convolution. And then the orbital velocity, which is the observable quantity that we can use to check our solution. And using this, we were also able to match the analytical solution from our collaborator, which was great. In the future, we'd like to adapt this for non-radially symmetric problems because a lot of the applications of variable order fractional Laplacians aren't radially symmetric. Maybe switch from MATLAB to Julia or something else that would make the code a little bit faster. We could also work on trying to implement our radial Fourier transform using FFT, just because it's a little faster in some cases. provided that k is decaying quickly enough. And then another project could be to use machine learning to try to find the distribution for S of x using observation of these orbital velocities that I mentioned. Yeah, so that's it. Thanks very much for your time. Thanks to the organizers for letting me present this.